Welcome back, everyone. So in our last few videos, just kind of recapping, we've talked about a variety of topics. We've talked about reaction kinetics, descriptions of reactions at equilibrium, and with both of those two topics, there's a lot of different concepts that are bouncing around. So I thought that over the course of the next two videos, I'd kind of have our focus be more on something that is applicable, that gets used in the biochemistry world. So with this first video today, I want to talk about protein-ligand binding and some pretty useful descriptions that we have of protein-ligand binding that are really rooted in our understanding of rate kinetics and equilibrium. So, for this instance, consider a protein, okay? Now, this protein is a biological entity that serves some function, and it does its functionality by binding to some sort of thing that we call a ligand. Okay, so we'll call this protein. Kind of looks like a Pac-Man guy eating a little pizza slice or something like that. So we've got our protein and our ligand, okay? And so these two are going to come together, kind of indicative of a sort of lock and key model here, but those will come together and they'll form this whole protein-ligand complex, okay? And we'll call that PL. Now, let's sort of idealize the situation and say that this forward reaction, which has a rate constant that we'll call Ka, that is the association reaction. And we're going to say that that's first order with respect to P, with respect to L, so it's overall a second order reaction. So if we wanted to write down our rate expression, we know from our discussion of integrated rate laws and noting the information that I already gave you, is that the rate of the association reaction is dependent on that association rate constant times our concentration of protein and our concentration of ligand, okay? Now, if we wanted to talk about this reverse reaction, we'll call that the dissociation reaction. We call it the dissociation reaction because that's the point where this protein-ligand unit is dissociating back into separate protein, separate ligand, okay? And that will have a kinetic expression, Kd times the concentration of PL. Okay. So that was sort of our kinetics description of what's going on in this overall reaction, okay? But notice that we have equilibrium arrows here, so this is an equilibrium system, and we can model this system using, so this will be a capital A, so the equilibrium association constant, so if we're kind of reading this reaction going this way, is going to equal our concentration of PL, so concentration of products over the concentration, the products of our concentration of reactants, right? Products over reactants. Okay, so again, that was kind of, if we were looking at the association, if we were reading this reaction kind of going this way. If we read it going this way, then we're worried about an equilibrium description of the dissociation, and that is the equilibrium dissociation constant, which is really just the inverse of all this. So that is equal to 1 over, and again, it's equilibrium, so we're going to use capital K's here, capital KD, okay? So again, just to kind of recap, this is kinetics. This is from equilibrium. All right. Okay. Lots of fun looking at that Pac-Man guy. So, why is this useful? How does this get applied into the sort of biochemist's toolkit? Well, one thing that's really useful in knowing is if we have a certain amount of protein and a certain amount of ligand sitting in a cell, it's useful to know how much of that protein is bound to the ligand, right? And so what that really means is that we're looking at the fraction of occupied binding sites. Okay? And this number gets represented symbolically with a theta. And so, you know, if you're good at rationalizing math problems, you might be thinking, okay, so what would it mean to have the fraction of occupied binding sites, the fraction of bound proteins? So that's going to be the concentration of our protein-ligand complex over the concentration of the protein-ligand complex plus the concentration of unbound proteins, right? So, you know, we're looking at this cell at some point in time and we're able to tell, okay, look, there's some amount of protein here that is binding to a ligand, and there's some amount of here that isn't, right? So, but this is a little cumbersome to determine experimentally, and you know, we would like to have something that is, you know, just easier to work with. Well, you know, looking back at our rate laws and also our equilibrium expression, we are going to actually be able to make this expression into something that's way more easier to work with empirically, and we'll even get to do some problems with it. So, what we're going to start out by doing is noting that our concentration of so remember, at equilibrium, we've got sorry guys, looking over my notes. So looking at, our equilibrium, we can rearrange this and say that, so we had Ka equals L. Sorry, I'm just gonna delineate this a little bit. Right? So if we multiply this denominator on both sides, what we get is that the concentration of PL is equal to Ka times P times L. Okay? And what we're going to do is we're going to plug this guy in back up here. Okay? So then, that leaves us with our fraction of bound sites being equal to Ka L over concentration of PL plus concentration of P. Alright, and then our next step is eliminating P. So going back here, again, we can change this concentration of PL at the top. We can also go in and change it right here, right? Pretty basic algebra. Nothing to get too intimidated with, so I'm going to rewrite that to Ka P L Ka L plus P. Alright, so we've got some stuff that we can factor out here. So these P's, those will all go away. Which will leave us with plus 1. And then if we go back to what we said and said, hey, look guys, so this is the equilibrium association constant. The equilibrium dissociation constant is just the reciprocal of this value, right? So we can go back in and apply that here. And when we do some handy-dandy rearrangement, what we end up with is theta is equal to L over L plus KD. So just in case you all were lost there, the sort of operative step that we took from getting to this point was recognizing that that Ka is equal to 1 over Kd, and then just do some algebra. Rearrangement. Pardon me if I spelled this wrong. Okay, so great. Now we have a really useful way of talking about what our fraction of bound proteins is, right? Because look, we can pretty easily control how much ligand we, have, and we can experimentally determine KD for various protein ligand situations. Okay. So just kind of a recap of what our reactions are, or not what our reactions are, but what our sort of reaction descriptions have been. We've said that first, so we have PL, P plus L. That's this protein ligand complex, Ka, little kd. So we've said that at equilibrium, so given enough times where this reaction situation has been able to achieve equilibrium, we know this is true. We also know, again, this is capital K, so the equilibrium association constant is equal to the reciprocal of the equilibrium dissociation constant, and that is equal to that. And we know that theta, the number of bound protein sites, is equal to P, the concentration of the PL complex, plus the concentration of the PL complex over the concentration of P, right? And then we were able to say, oh, so if we wanted to have a more experimentally friendly way of writing that out, we could say it's equal to the concentration of the ligand over the concentration of L plus this value of the dissociation equilibrium constant. Okay? So again, this we got from kinetics. This we got from our equilibrium discussions. And this came from just being smart biochemists. It just takes a little bit of intuition. So now we have sort of all the theoretical tools to do some biochemistry problems that you might be confronted with that, just involve equilibrium and kinetics, okay? So let's start by looking at, so this is sort of really a multi-step problem of one situation. So a protein has binding affinity for its ligand, a peptide, which is just a chain of amino acids. A protein itself is actually a polypeptide chain. So it has a binding affinity of Ka equals 2 times 10 to the 5th inverse molar at a pH of 5 and 25 degrees Celsius. At what concentration of the ligand is half of the protein bound? Okay. So we got a few operative phrases that we need to look at. So what is this question asking for? It's wanting to know at what concentration of ligand, right, is half of the protein bound, okay? right, so does that make sense? We know then half of the protein is bound, so theta needs to equal 1/2. Okay, and what we're wanting to know is at what concentration of L of ligand do we get that sort of situation, okay? All right, so what is an equation that we have that relates the fraction of bound protein and the concentration of ligand? So if we look back at our equations, okay, you'll notice that this bottom equation, not so much this stuff, but this in particular is really what's going to be important here, right? Because we have an equation that relates fraction of bound protein and the concentration of ligand. The only thing that we're missing is this KD value. But oh wait, you say to yourself, that's not too hard to compute because we were given our association equilibrium constant, right? So we said that Ka was equal to 1 over Kd. Therefore, Kd will just be equal to 1 over Ka. Okay. So now let's get to the calculation aspect, and I forgot my calculator, so I'll be right back. Okay. So what I would recommend as the first step here is to find KD. So KD is equal to 1 over Ka, which is then equal to 1 over 2 times 10 to the 5th molar. So then that, you know, if you're unsure of what that'll equal, just plug it in on your calculator. It's also not that bad of math, but that will equal 5 times 10 to the negative 6 molar. So remember, our units are inverse molar, but we're in the denominator here, so that is what our dissociation equilibrium constant will be. Okay, great. So we have this value. We know that theta is going to be equal to 1/2, which will be equal to concentration of L over L plus KD. Okay, and so we rearrange that. So just figuring out the best way to write this out. What we get is that L is going to be equal, actually, to 5 times 10 to the negative 6 molar. Okay? So that, my friends, is our answer. Okay? And just so you know what I did here, to To get from here to here, I multiplied denominator on both sides, and then to get from here to here, I just solved for F, concentration. Okay, great. So now the second question is, what fraction of protein is bound at ligand concentration of 0.75 micromolar? So, a little bit different. Now we're wanting to know what the heck our fraction of bound protein is, given that we know that the concentration of ligand is equal to, and I'm going to just go ahead and get our units back to sort of standard units. So we have 0.75 times 10 to the negative 6 molar. 10 to the negative 6 molar is micro. And then putting that into scientific notation, we will do that. And so that is 0.75 times 10 to the, okay, yeah. 10 to the negative 7. Okay. Yep, that looks good. Okay. And this time we don't need to worry about our KD because, you know, this is just kind of working off our work from the top half. So, theta is equal to just to kind of reiterate that, bring that home. And we have 7.5 times 10 to the negative 7 molar. Okay. That will then equal just a moment. Gives us a value of 0.13, okay? And so that is all that has to go into those two parts. So just to kind of make sense of what that's saying, that means that when the ligand concentration is at 0.75 micromolar, only 13% of all the protein in our cell that we're looking at is bound. At what ligand concentration will 90% of the protein be bound? So this is kind of, you know, really just like the first question. We have a ligand concentration of 90%, or sorry. We have the amount of protein that is bound is 90%. So, you know, converting percents back into fractions, that means that theta is equal to 0.9. And we're wanting to determine when does this happen given some sort of ligand concentration. what is the ligand concentration necessary to get that fraction there. So again, just going to do our process here. We have plus 6 molar, rearrange. And so I'll divide by 0.9, and rearranging, that gives us 5 times 10 to the negative 6 molar is equal to 8 times that. So and so this happens when oh, is that good? Can't do algebra. Don't trust me. Okay, so yeah, disregard that. So what I did is I just distributed those out, and then so here subtracted our L terms, and then just divided. And so what that means is that at 45 micromolar, 90% of the protein will be bound. Okay. All right, and then our last question is a little bit less quantitative. We're not going to be computing as much as just kind of conceptually wrapping our heads around what's going on when we have these protein-ligand binding situations. So what this experimenter did was he or she or they raised the pH to 7.0, and what was found was that the dissociation constant was 10 micromolar. So I'll call this KD nu is equal to 10 times 10 to the negative 6 molar. Is the binding tighter or weaker at this pH compared to the pH of 5.0? And how, why do we know that? So just to kind of refresh our memory here, our old KD, or our KD at, maybe you could think it at, and this is in blue just because, it's what was given to us in in the problem. This we had already experimentally found to be 5 times 10 to the negative 6. So when we increase the pH, the equilibrium dissociation constant decreased to 5 times 10 to the negative 6, right? And so what that means, right, is that looking back here, what this means is, or what would be even better is, since we had said that KD, or the reciprocal of KD is equal to KA, what we can rearrange then is we can say, well, KD really equals the concentration of non-bound protein and non-bound ligand over the concentration of protein-ligand complex. So what this is saying is that at this new pH, we have even more unbound protein and unbound ligand than we have more products than we do reactants, right? So in this instance, because we raised the pH, the binding of the protein is weaker. Because KD at, sorry, that should have been a lowercase b, at a pH of 7.0, maybe shouldn't say yields, indicates a higher concentration of unbound protein. Alright guys, so that is the end of our first part of applying equilibrium and kinetics to some more applicable biochemistry. What we have kind of learned today is just going over the general reaction mechanism of what happens when a protein binds to a ligand and forms a protein-ligand complex. We talked about the rate laws that are associated with this sort of system, and those, were descriptions that came from kinetics. Then what we also talked about was just the equilibrium situation of this reaction setup. And so we have our equilibrium association constant is equal to this. And then what else we talked about was that the dissociation constant is really just the reciprocal of the association constant. And we also talked about a really useful analysis when we're looking at proteins that helps us determine the number of proteins that are bound or to a ligand. And so that description we said was equal to this, and then from this and applying our kinetics and equilibrium jazz, we were able to make a really useful relation here that uses the concentration of ligand and the dissociation equilibrium constant. And then from there we were able to do some awesome, computative work. So yeah, that's the end of today's video. Thank you all for watching.